Hello, my name is Kevin Craig. This is a live tutorial on the use of LabVIEW to create a dynamic numerical simulation of the spring pendulum dynamic system. The mathematical model of the spring pendulum dynamic system consists of two coupled nonlinear ordinary differential equations. This is the starting point for this tutorial. Once I have the equations, I then can use LabVIEW to solve the equations for any initial conditions and show plots of the predictions from this mathematical model. Let's begin. I've opened up LabVIEW 2017, my RIO. RIO stands for Reconfigurable Input-Output. This version of LabVIEW has special features for the myRIO, which is a real-time control device, and it makes programming for real-time control much easier with these additional features. For our use here, it is of no concern. Basic LabVIEW can do what we need it to do in solving these coupled nonlinear ordinary differential equations. I begin by moving my cursor to File, and I left click and choose New VI, Virtual Instrument. I see that two windows open up. One is the front panel. The back is the block diagram. In the block diagram, we do all of our graphical programming. In the front panel, we have all of our inputs that we can specify on the fly as the simulation is running, as well as all of our output graphs. I begin with the block diagram. We can go from one to the other by selecting Window and then Show Block Diagram. Window, Show Front Panel. So for now, I'll just use the block diagram and I'll keep the front panel in the background. I'm going to make the block diagram a little bit larger. Fill our recording window. And this is where I will begin my block diagram graphical programming to solve the equations. I begin by right-clicking anywhere in the white space and going down to the bottom and selecting Control and Simulation. Then moving over to the right to Simulation, and then to Control and Simulation Loop. I left click, and then I create my Control and Simulation Loop. I can center it on my window. Within this loop is where we will build our block diagram. As we are running this in simulation time, with a simulation time step we will specify. If I put my cursor on the black border and I right click, I can scroll down to configure simulation parameters. Left click. I can set the start time and the final time. I'll make the final time 60 seconds. I want to use a fixed step size. I'll pick a fixed step algorithm rather than a variable algorithm. I pick Runge Cutter 3. Many will do. My step size, I will make 1 millisecond. And that is all I really need to change or set in my configuration simulation parameters window. The start time, the final time, the solver, and I pick a fixed step size only because I want results at fixed intervals in time for comparison purposes. And the step size I usually pick as 1 millisecond unless for some reason I need to use a smaller step size, and rarely do I use a larger step size. When I'm done, I can just go to the bottom and click OK. Now all of my programming will be done in this window. The procedure is to start with our two equations and create the two stems that will take us from the highest derivative to the variable. In this case, my two variables are r and theta. So my two integrators will take me from r double dot to r and from theta double dot to theta. If I right click and I proceed down to control and simulation, simulation, continuous linear systems, integrator. And I'll put an integrator in that position. Let me resize it right now. And let me just click on this name and let me just call this integrator 1. Now this integrator will need to have an initial condition. If I right click on it, I can better yet, let me double click on it and let me choose here parameter information, parameter source. Let me choose terminal. The advantage of this is that I can set, and I'll hit OK, is that I can set the initial condition from the front panel rather than having to set it in the block diagram. And this will then allow me to vary the initial conditions as I wish from the front panel without having to go back into the block diagram to make the change. So you can see here now there are two inputs. One is the initial condition and the other is the input to the block. What I'm going to do is just highlight this and type Control C and then Control V to duplicate. Control C, Control V. I'll create my second stem, and again, Control V, and I'll get my fourth block. There are many ways to replicate blocks, but now I have my two stems. I will connect one to the other, and the way I do that is I bring my crosshair to the output of one block. And I move to the other block, and I connect. And similarly down here between integrators 3 and 4. This first stem will integrate theta double dot to give me theta dot, which will then give me theta. The second stem will integrate r double dot to give me r dot. Integrated again will give me r. I can label this by just typing in that this signal will represent theta dot, and this signal will represent r dot. This helps me to identify my stems. The more you can annotate your block diagram, the more usable it will be, more informative it will be for any users. I'm going to now switch to the front panel. So I'll just go to Window, Show Front Panel. Now in the front panel, I'm going to right-click, go to Numeric Control, and I will place a numeric control here on the left portion of my front panel. And I'm going to rename this to be R underscore initial. This will be my R initial condition. And if I right click again, numeric control, place it underneath that. And again, I'll rename this theta underscore initial. And I'll have to make this block a little bit bigger so I can see that whole name. Right click again, numeric control, and I will name this R underscore dot initial. And once again, numeric control, and I will call this theta underscore dot initial. So now here I can specify my initial conditions for R and theta, for R dot and theta dot. So let me do that now and enter these. The initial R for our simulation will be 0.115 meters, and for theta, it will be 0.021 radians. All angles are measured in radians. The initial R velocity will be 0. The initial theta velocity will be 0, so I can leave those the way this is. Let me correct this. This is 0.115. If you now go back to the front panel, or excuse me, the block diagram, you'll see that these now appear. So now I can connect these to my integrators. This is R initial, and so this will get connected here, the initial condition for the integrator that takes me from R dot to R. This is R dot initial, and this will take me from R double dot to R dot, and that's where the initial condition goes. This is theta initial, and I similarly make that connection here. Theta initial, this is theta dot initial, and I'll position that accordingly right here. Now I have my integrators that will integrate my variables and take me from theta double dot to theta dot to theta, R double dot to R dot to R with the appropriate initial conditions. Once I've done that from the case study, you know that the next step is to simply do what the equations say. So let's begin by creating the equation for theta. So theta double dot equals 1 over L plus R times the sum of two terms. So before I do that, so we don't have to go into the block diagram to change numerical values of parameters, let me go back to my front panel and let me create the constants which I can vary on the front panel, which I need to run the numerical simulation. So again, right-click, numeric control. And I'll place that here at the top. And this will be my spring constant K. And I already know what that spring constant is. It's 172.8, and that's newtons per meter. Remember, LabVIEW is not keeping track of units. We have to keep track of units. Then I will right-click again, numeric control, and I'll place a block underneath that. And this will be mass M. And mass M I know to be in kilograms 1.815. I'm just going to highlight all of these other blocks and just move them down a bit and line them up. Maybe I'll do it down a little bit farther down here. I'll right click again, numeric control, and my next block then is spring length. Call that capital L, and I know my spring length, free spring length is 0.333 meters. And then lastly, numeric control. Last parameter I need is the pre-tension FT, the pre-tension force, and that's 5.71 newtons. Let me just move this down a little bit. So you can see I have now my parameters which I can change at any time from the front panel, along with initial conditions which I can change anytime from the front panel. And you can, again, do some rearranging as you see fit. If I go back now to my block diagram, and I can just see it's underneath, I can just go back and click on it. I can see that here are at the bottom are the blocks that I just brought in to the front panel, and now they appear on the block diagram. So I'm just going to bring them into the control and simulation loop. And I'll use these to then build my block diagram. So the first equation says that theta double dot is 1 over L plus R. So I need to create the sum of L and R. So let me highlight all of these and just move these all to the right a tiny bit. Give me some room to work. I'll right click. I'll scroll down to control and simulation, signal arithmetic. I'm going to grab the summation block. Let me do that again. Right click, control and simulation, signal arithmetic, and I'll grab the summation block. So this is my summation block, and I'm just going to rename this right now as sum L plus R. So I know what I'm doing here. If I double click with my left button, I only have two inputs, and they will both be plus. So I'll say OK, and I'm going to make this a little bit bigger. I'll grab one corner and make it a little bit bigger. So I have these two inputs. I'm going to move the label off to the side, L plus R. So here's my spring length L, and that needs to get connected to one input. And the other is R, which is this output here. This is R. So I'm going to bring If ever we get wires that are in error, like we show here, Control B gets rid of those wires. So now I will grab the output of this. This is R, and I'll bring this around, and I'll input this into the plus of that summing junction, and then I'll take the spring length here, and I'll input it into the plus of that summing junction. So the output of that summing junction is L plus R, but I need 1 over L plus R. So I'm going to right click, and I'm going to go to numeric, and I'm going to find in the numeric the reciprocal, 1 over X. I'm going to grab that, and I'm going to put that right here. So in other words, this will give me, let me move this over a little bit, this will give me then 1 over L plus R. Now the equation says 1 over L plus R times the summation of two terms. So I will right click, control and simulation, 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 signal arithmetic, summation block. I'll put a summation block here. I'll make it a little bit bigger. And I'm going to rename this as sum and then theta underscore double dot, as this will give me the output will be theta double dot. Both of the inputs into this will be, and there are two, will be minus. Now, the output of this will then get multiplied by 1 over L plus R. So I'll right click, go to numeric, go to multiply. Grab that and put that right here. So I want to multiply the output of the summation block with the output of 1 over L plus R. So I weave my way to make that connection. Let's try to make this a little bit easier to read, and we do. And so the output of this then will go into my integrator block, the input. So now 1 over L plus R times the output of this summing junction. Now what's the output of this summing junction? The output of the summing junction is minus 2 times R dot theta dot. So let me go here, right click, scroll down, control and simulation, simulation, signal arithmetic, gain block. I'll put a gain block at the top here. I'll right click on it, and I want to reverse the terminals. I want to flip it around. And this has a value of a gain of 2. And since that doesn't change, because that's part of the equation, it's okay for me to leave that hardwired into my block diagram. Now I need to multiply R dot and theta dot. So I will right click, go to numeric, and I'll proceed to, no, I think we will go to use another multiplication. Let's right click, scroll down to control and simulation, simulation, and then we can go down to let's see what where we can. There are many options that we can use. So let's back up a minute. Let's right click, numeric, and we want to multiply. And we can rather than I just want to give you another option. So let me back up again. I apologize, but this is real time. Let's go to control and simulation again. Go to simulation, go to nonlinear systems, or go to linear systems, signal arithmetic, rather go to signal arithmetic and multiplication. So I'll use this block. Again, it's not the only block I could use, but it's the one I'm choosing to use right now. I'll right click on this, I'll reverse the terminals. I'll connect the output of that to 2, and I'll connect the output of that to the negative input of the summing junction. And I'm going to move the label for the summing junction off to the side. Now, this multiplies 2 times the product of 2 inputs. One input is theta dot, so I'll put an X at the input and just meet the line for theta dot, and you'll see a node appears. And then I'll do the same thing for R dot. I'll come across, and I'll just come straight down to R dot. I'm just going to move this label off to the side a little bit. And I'm going to move this line off to the side a little bit so we can see that. So this says take R dot, theta dot, multiply them together, multiply it by 2, bring it into the summing junction with a minus sign. And so I do that. Now, the other term is G sine theta. So let me right click. Let me go to control and simulation. Simulation. Let's see, rather than that, let's go to numeric, or excuse me, let's go down to mathematics. Mathematics, and we'll go to numeric, elementary, trigonometric. And we want the sine, and then we'll do the same thing again. We'll go to mathematics, numeric, elementary, trigonometric, and we want a cosine block. So as you see me searching for blocks that I need, this will become easier for you the more you use LabVIEW, as the menus are very layered, can go several menus deep, have many features. You'll be able to do anything conceivable with LabVIEW, but it may take some time for you to find the right blocks. You can always highlight a block and hit Control H, which will show you, and you can't see it because it's out of the window for recording, a context help. So for any block, you can always hit Control H and it will tell you about that block. So I have cosine and sine, and it will take the cosine and sine of that in radians. So I will take theta, which is the output of this block, and I will connect the output of that to the cosine block. And then I will take the input to the sine block and just connect to that line. So now I have theta going into cosine and sine, and the theta is in radians, and it will take the cosine and sine in radians. I need to multiply this by g, acceleration due to gravity, which won't change. So what I'll do is I'm just going to go to control and simulation, signal arithmetic, a gain block. And I'll put a gain block here and I'll make the gain block 9.81 for its parameter, 9.81. Hit OK, and we can leave it labeled as just a gain block, highlight it, Control C, Control V, and get another one. So now I'm multiplying each of these blocks by G. I can make my control and simulation loop a little bit bigger. And I can connect the output of the cosine to 9.81. Similarly for the sine to 9.81. Because I know I need both of those for my equations. So this is then the sine, this is the theta times the sine of theta times G, sine of theta times G, and this has to come in, which I can work around like this. This has to come in here with a minus sign. So now I've completed that equation, and now the best way for me to check to make sure that I've done this properly is to write the equation from the block diagram. This says here, this line here is theta double dot. Theta double dot equals the product of 1 over L plus R times, and this line is coming from, let me just delete this and reconnect it. This is coming from the sum. Sometimes if the lines appear to get blocked, you're better off deleting them and reconnecting them to make sure that they are connected to the right blocks. This is the sum of G times the product of theta dot and R dot. Comes in with a minus sign, and then minus 9.81, which I forgot to connect here, so let me do that. I seem to have misconnected something here, so let me hit Control B. So this has to go like this. Let me delete that line. This is sine theta, so this is going, I connect this around like this. So this is minus G sine theta. Okay, so it appears I have the theta double dot equation correctly built. So now let's do the R double dot equation. R double dot equation says I have 4 terms. So I will right click, go to Control and Simulation, Simulation, Signal Arithmetic, Summation. And I'll make this summation block a little bit bigger. And I'll double click on it, and there are 4 inputs. There are 2 plus inputs and 2 minus inputs. So I have plus, minus, minus, plus. And the output of this is R double dot. So I can just connect that directly to my integrator, which is right here. So what goes into my integrator? The first is G cosine theta with a plus sign. Here is cosine of theta times G. So if I connect this and bring this down and over, and this comes in with a plus sign, plus G cosine theta. Now I have a minus pretension over M. So if I right click and I go to numeric and I go to divide and I put a division block here, I want Ft divided by M. So here's my pretension and here's my mass. So if I connect the pretension to the first input of the division block and the mass to the second input, I get ft over m, which goes in with a minus sign, minus ft over m. Next, I have minus k over m times r. So I have my spring constant k, and I want to divide that by m and multiply that by r. So one way to do this is to, many ways to do this, of course. So what I'll do is I'll right click, I'll go to Control and Simulation, Simulation, Signal Arithmetic, Gain Block, and I'll put a gain block down. I'll right click on the block and I'll reverse terminals. I'll label this as K. I'm going to double click on the block and select terminal. And I'm going to connect my spring constant terminal to that block. And there's a input for it right at the top. So now I can set what K is, and K gets multiplied by R, and I can connect the input to this to R, which is this signal right here. So this is K times R, which I then have to divide by M. So I can right click, numeric, division. So I'll take a division block and I'll put it here as this comes in with a minus sign. And I'll connect that to the minus input. And I have, so K will go into the first input. And it's K divided by M. And M will go into the second input. And I can just pick off M from right here. So it's K over M, K times R divided by M, and it goes in with a minus sign. The last term that comes in is L plus R times theta dot squared. So I will right click, go to numeric, go to squared, and I need a theta dot squared, and I'm multiplying that by L plus R. So I have then theta dot, which is right here. So I'm going to take the input of this and wind that around here to theta dot. The output of this then is theta dot squared. And then I need to multiply that by, so here I can use a different multiplier. I can just right click, numeric, say multiply, and I can multiply theta dot squared by L plus R. And I already have L plus R, which is the output of this line right here. This is L plus R. So I can just take the input from this and just go off and pick it right from this interconnection. Let me separate these lines a little bit so we can see which line is which. That seems to work. Let me move this over a little bit. And then the output of this then, which is L plus R theta dot squared, needs to be brought down. And over to my plus input. Lines get a little bit crossed here. You can do a better job of laying these out on your own, but they're easy to follow. Let's make sure now that we have created our R equation properly. This is R double dot. R double dot equals the sum of this term here, which is the product of L plus R times the square of theta dot, then minus what? Minus K times R divided by M, K over M times R, minus pretension Ft divided by M, and then plus G cosine theta. So my equations are correct. Now I need to create some graphs for my outputs. So let me right click, go to Control and Simulation, Graph Utilities, SimTime Waveform. And I'll put 1 there. And then what I'll do is I'll Control C, Control V, and I'll put another one down. And the first one I will label as theta. And the second one I will label as R. So we'll say R versus time. And we can say theta versus time. Now we can go to our front panel, and I can see that I've created these 2 graphs which are off to the side someplace, and I'll now just position them and maybe resize them a little bit, make them a little bit bigger, try to keep them the same size. Let's move them over. I've got some room over here to the left. And now I have an idea of what the scale should be. I know for time, it's going to be 0 to 60 seconds. So I'm going to right click on this graph, and I'm going to go to X scale, make sure the auto scale X is not checked. So I want this to start at 0 and I want this to end at 60. Similarly down here, I want this to start at 0 and end at 60. Make sure that check the X scale to make sure auto scale X is not checked. And for the R versus time, I know that the values are going to go from minus 0.15 to plus 0.15. So I'll go to the Y scale and I'll uncheck the auto scale Y. Then I'll double click here and I'll make this 0.15, and the bottom minus 0.15. Hit enter. Similarly for the theta, I'll right click, Y scale, make sure the auto scale Y is off, and I'll click this and make this 0.25 and minus 0.25. So now I have my graphs that will plot R versus time and theta versus time. Lastly, I'd like to create a graph that would plot R versus theta. And this would show what I would see if I attached a laser light to the mass and had it project on a screen and actually trace out and leave the path that it followed on the screen. This is what you would see the path of the mass actually going through, executing throughout its 60-second motion. So what I will do is I will go back to my block diagram. I can find it here. And but first let's connect theta to my graph. So I'll just put the cursor here at theta and connect it to theta. And the same thing for R. Connect this to R. Now I'll right click, go to Control and Simulation, Simulation, Graph Utilities, Buffer XY Graph. And I'll put down this XY graph buffer. I'm going to double click on it. Well, that took me to the, let's go back to the block diagram. Let me double click on the front end of it, and where it tells me the buffer size. And the buffer size is very, very small. I'm just going to make it a very large value. I'm just going to make it 1,000,000. And so I have all the data points because I have 60, because I actually have 60 seconds. I actually have 60,000. So I can make it 100,000. 100,000, 100, 1, 2, 3 should be fine. Let me go to the front panel, and here's that graph. Let me bring it here. Let me resize it. Let me center make sure I'm still on the screen, and I'm not. So let me make it a little bit smaller, my XY graph, and bring it here. Try to keep everything on the screen. I can make my my front panel a little bit bigger. Okay, so that's a little bit better. Let me make this a little bit bigger. Let me relabel this. Let me call this this will be R versus theta. So this is R versus theta. R on the x-axis, theta on the y-axis. Let me right-click. Let me look at X scale and take off the auto scale X. And I know this is going to vary from minus 0.3 to 0.3. And we'll make the y-axis. So we'll right-click, go to Y scale, take off the auto scale Y, and this will go from 0 to minus 0.15. So I have my graph, R versus theta. And let me go back now to my front panel. Now let's go back to our block diagram, which I'm at. And now I want to plot not R versus theta, but actually minus R versus theta. So let me right-click, go to Control and Simulation, Simulation, Signal Arithmetic, Gain block, and let me put a -1 for my gain block, -1, and let me connect R to it, which is this. And so this will be minus R, and I need to plot minus R versus theta. Now the way I need to do this is I need to use what is called a cluster. So I'm going to right click and go over here to clusters, and I'm going to use a block that's going to take my two double precision numbers and put this into the graph. So I'm going to bundle these two, and I have two inputs. So the first one, the top one will be um, the top one will be um, the top one will be the top one. Let's I'm not so sure. The top one will be let's see, the bottom one here I'll make minus r, and the top one will be theta. So that goes up here like this, and this is theta. Then the output of this then will then get connected to the input there. I included in the case study top 10 things you should know about LabVIEW. One of the most important things is to learn all about the wires in LabVIEW. The thicker the wires, the more data they cover, they carry. So here we have our two variables going into our R versus theta graph. And I have R and theta, X and Y. So it appears I have theta on the x-axis and R on the y-axis. So I probably should rename this to be theta versus R. Okay. I think now that we have, that seems to be our complete diagram. And if we go to the front panel, we'll see our graphs are there with all of our parameters. And the only thing left now is for me to run this. So if I run this, so you see my simulations. You see in this graph the R versus time and theta versus time. And here we have theta versus R. And with theta on the x-axis and R on the y-axis, as I explained. And these are the same plots that appear in the case study. So here is our front panel, and I can change any of my initial conditions. I can change any of my parameters and rerun the simulations right from the front panel without going back into the block diagram. I can go back to the block diagram, and you see I have it all laid out. To make sure your block diagram is correct, you need to write the equations of motion from the block diagram. There's no reason why the block diagram should ever be incorrect, because you can always verify it by just writing the equation of motion from the block diagram. The equations might be incorrect, but the block diagram should never, ever be incorrect. So let me go back to the front panel then. So this then concludes the live LabVIEW tutorial on how to solve the two nonlinear coupled ordinary differential equations corresponding to the spring pendulum dynamic system. Thank you for your attention.